Good afternoon, everyone. My name is Chi, and I'm from University of Houston. Today, I'm going to talk about the fast integral equation method for EM modeling of the energized casings and the reservoir fluids in late formation. This is my outline. I'll begin with a brief introduction of the background and the motivation, and then I will talk about the challenges of this problem. After that, I will talk about the method, including the basis function, the electric field integral equation, and sink electric assumption, and also the PMCHWT scheme. And after that, I will show some simulation results. And finally, I will draw the conclusion and some possible future work. Actually, this work is inspired by a hot topic in geophysics named carbon dioxide capture and sequestration, also known as CO2 sequestration. So the basic idea is the CO2 is captured and temporarily stored on the ground, and then it will be injected in a deep reservoir through this injection well. After injection, this well will be sealed, so the CO2 will be stored on the ground. There are a couple of purposes of this CO2 sequestration. For example, it can reduce the CO2 in the atmosphere, so it will mitigate the global warming, since the CO2 is a green gas. And also it can enhance the oil recovery, especially in the deep reservoir. And also it can be carbon cycle. The carbon will be transformed to other natural resources. So from different point of view, this is a promising idea. However, this CO2 will leak out from this deep reservoir, either from this injection well or from other fracture fault due to the movement of the formation. So we need to monitor the status of this CO2 plume. Here we have two approaches. First one is using the surface sensor, and second one is using the monitor wheel. This is the energized casing. So we need to do the EM modeling to determine which method is more feasible. Although some commercial packages and solvers have already been developed, the EM modeling of this problem is still challenging because this is a multi-scale problem. It contains the energized casing, which is a single structure, and also this multi-layered coating on the drilling pipe. Besides, the energized casing and the CO2 plume are embedded in the layered veneer. So if we consider the partial differential equation solver based on the finite difference method or finite element method, there are two problems. First is the discretization problem, especially for the multi-scale structure. You can see in these two figures. There will be a large number of unknowns, so the system matrix will be very large, and the solver will converge slowly. However, these problems can be avoided if we consider the integral equation method, because we only need to do the surface discretization. For example, the energized casing will be discretized by segments, so the number of unknowns will be reduced significantly. And also, we can use the layered medium Green's function to handle this problem in the layered formation. Before I talk about the details of this approach, I will first introduce two basic functions that will be used. As I mentioned, the single structure will be discretized by segment. So here, we use the linear basis function. However, for the CO2 plume, which is a surface structure, so we need to use the RWG basis function. So using this basis function, the continuous current density will be discretized. Here I will show some details of the energized casing modeling. So the energized casing modeling can be regarded as a EM scattering problem from PEC. So if this energized casing is not perfect conductor, so we can introduce the surface impedance, and then this will be not there. Actually, this is based on the boundary condition of the electric field. That is, the tangential electric field will be zero. So this we call this electric field integral equation. So for the energized casing, which is a single structure, So the radius of the casing will be much smaller than its length. So we can use this simple assumption. That is, the current only has the axial component, and the current is invariant as mutually. So under this assumption, so we can reduce the surface integral to the line integral. So in this integral, the k is single kernel, which can be evaluated by the quadrature rule. Regarding the coating modeling, we can use the thin differentiate assumption. That is, we only consider the normal component of the polarized current. So in each layer, we have this polarized volume current, and then they remain constant because each layer is very thin, so the variation in this direction is ignored. We also have the polarized surface charge on the boundary of each two adjacent layers. In the inner boundary, we have this induced surface current and the induced surface charge. So we have 4 unknowns in total. However, we can use the equivalent volumetric principle to relate the polarized current with the electric field, and then we can use the boundary condition of the electric field to express this polarized current using the surface current. Similarly, we can use a quasi-static approximation to approximate the polarized surface charge using the surface current. And then we can use the electric current continuity equation to express the surface charge using the surface current. So finally, we only have one unknown. That is, modeling the coating doesn't increase the number of unknowns. Here we show the modeling of the reservoir fluids, and we use the PMCHWT approach. Actually, this name is formed by the first character of 6 people, and it applies the equivalence principle, including the exterior equivalence and the interior equivalence. Here we assume we have this original problem, and there are electric and magnetic current both inside and outside this domain, and these currents produce E and H field in the entire region. So first we can use the exterior equivalence, and we introduce the equivalent current in the exterior boundary of this domain, and so together with the expressed current, so they just produce the identical electric field outside this domain to the original problem. However, the E and H field is 0 inside this domain. Similarly, we can use interior equivalence to introduce equivalent current in the interior boundary of this domain, and together with expressed current inside this domain, and they just produce the identical E and H field to the original problem. However, the outside this domain, the E and H field are 0. So if we put them together, we can get the original problem. Here we have to satisfy the continuity condition. That is, the E and H field should be continued across the boundary. So we have this continuity equation. This continuity equation is the continuous form. So this J and M are the continuous current density. So here we need to discretize the J and M using the basis function. So we have this discretized form of the system matrix. Each entry they have the form of the integral equation. In the previous slide, I just showed how to model the energized casing and the CO2 plume separately. However, this is a mixed conducting and dielectric body problem, so we need to consider the coupling between each other. For example, the current on the PEC surface will produce E and H field on the boundary of the dielectric body, and also the current on the dielectric body will produce electric field on the boundary of the PEC. So because this EFIE and PMCHWT are based on the boundary condition, So we can see the coupling between each other. So this is the overall system matrix of this problem. In the green box, this is the system matrix of the EFIE, and in the blue box, this is the system matrix of the PMCHWT, and this red box accounts for the coupling between each other. The more details can be found in this reference. Here I show the layered medium Green's function. So in this grid box, this is a layered medium Green's function in the spectral domain. So we need to evaluate the Green's function in spatial domain. So first we just use the inverse Fourier transform together with some field identity to get the to transform this spatial domain, the medium Green's function, to the spatial domain. So we can then we can calculate the potential identities using the linear medium Green's function. And finally, we can use this mixed potential form to get the scattering electric field. Here I will show a synthetic example. So in this figure, you can see we have a 4-layer formation, and this is the coordinate system of each layer. And also we have the different connectivity for each layer. Here we can see the isotropic medium, so the horizontal and vertical connectivity are identical. And also we can see the invaded zone and the casing as a coating. The length of the injection well and monitoring well is 1,400 meters, and this is the radius of the well. Also, we have the parameter for the CO2, and this problem is the operating frequency is 20 Hz. Here I showed the results of the surface current on the casing. So in the left figure, this is current on the injection well, and the left figure shows the current on the monitoring well. Here we can see a very large current. This is the location of the gas source. So in this figure, we have 3 curves. One is the result from console, another one is our mass with coating, and the other one is our mass without coating. So we can see these 3 curves almost overlap, so which indicate first our mass agree well with the console, and also indicate this coating has very negligible effect on the injection well. However, if we take a look at the right figure, we can see our results with and without coating, the difference is significant. So we can see this coating has an effect on the monitoring well, and similarly, our results just agree well with the console. Here we show the results of the surface current and the fluid. In the previous slide, we just showed the geometry of problem. Here we use a thin cylinder disc as the reservoir fluid. So in this plot, on the upper panel, we show the results obtained by our method. And this subplot shows the electric current, and this subplot shows the magnetic current. In the bottom panel, these results are obtained by the console. So if we compare these two separately, and we can find the results by our method almost have the same pattern as the console. So, and then we can compare the computational cost, and we can find, although our method is less accurate than console, but it's much faster and requires very few memory costs, so which can be realized in a regular laptop. However, with console, you almost need a workstation. So, and also the accuracy can be improved by increasing the mesh density. Here we show the results of sensitivity study. This plot shows the normalized voltage versus reservoir fluid radius. We want to investigate when we change the size of the reservoir fluid, what is the sensitivity of two approaches. And the first one is surface observation, which is based on surface sensor. The second one is monitoring well observation, which is using the Energized casing. So we can find the sensor on the surface is less sensitive than the Energized casing, especially when this reservoir fluid is larger than a threshold. If this voltage doesn't change, which means the sensor will not detect the change on the ground. So we can see the Energized casing is better than the surface observation. Here we have some conclusions and future work. So the combination of the EFIE and PMCHWT scheme is applied to model the Energized casing and the reservoir fluids in the layer medium. And the induced current on the casing as well as on the fluid surface agree well with the console results. And the target application can be geophysical monitoring of the CO2 sequestration. So in the future, we want to introduce a junction basis into the current model. And also, we will parallelize the computation using OpenMP to accelerate the PMCHWT modeling. Here we want to thank for the support by the U.S. Department of Energy, Office of Science and Office of Fossil Energy. Okay, that's all for my presentation. Do you have any question? Thank you.